right. We've got one other little handy theorem that we're going to use called the conjugate roots theorem. It's a really simple theorem. I just wanted to show you something real quick with complex numbers. Okay, so a complex number, remember, has a real part and an imaginary part. Okay, so I'm going to multiply two complex numbers together. Okay, so this is going to wind up being 1, 2, 3, 4. So we wind up with AC plus ADI plus BCI plus BDI squared. Of course, the I squared turns into minus. And we get something that looks kind of like this. Okay, who cares? Well, here's the thing. If we multiply these two together, we're going to get a complex number because we've got these i's right here. Unless, if you can get AD plus BC to equal 0, then when we multiply these, we'll actually get a real number. So let's redo this real quick. And I'm going to put this in a very specific form. So these guys are basically going to be identical, okay? Except the real part is the same, but the imaginary part has its sign flipped. So let's see what happens when I do this. A squared minus ABI plus ABI minus BI squared, which is just plus B squared. Sorry. Now this looks very similar, except these are like terms, and they're a zero pair, so they cancel out. So if these are conjugates of each other, when you multiply them, you actually get a real number, even though we started off with complex numbers. Great, Mr. McClellan, who cares? Here's why we care. Look at this polynomial right here. Do you notice any imaginary parts, any complex anything? Nope. Now, here's the thing. When I factor this out, there might be complex solutions to this. But if you have all real numbers here, then that means that any imaginary solutions that you get come in conjugate pairs. So for example, if 7 plus 3i was a solution, and you had all real numbers here, then 7 minus 3i is also a solution. Okay, if I is a solution, then negative I is also a solution. They have to come in pairs. We talked about that a little bit with Descartes' rule, okay? That's why it decreases by 2 each time, because that's saying, well, these could all be real, or we could have a pair of imaginary, or we could have another pair of imaginary. They always come in pairs when you're dealing with these real numbers here. Okay, so here's how this is going to help us. We have this quartic equation. Oh, whoa, 4 roots? 4 roots, Mr. McClellan, you kidding me? Well, first of all, they went ahead and gave us one. So thanks for that. So let's take this guy out. So negative 5i, now 1, 6, 9, 150, negative 400. Okay, so 1, and then we have negative 5i. This gives us this. Then when we multiply this, we get positive 25, but the i's give us negative 25. This gives us negative 30i. Okay, so we get, what is that? Negative 16 minus 30i. We multiply again, I get negative 150. I get positive 80i. These cancel, I get 80i. I multiply these, I get positive 400, and I get a 0, which is good news because this was supposed to be a 0. Well, now I have this polynomial left over. It's a cubic. Oh, man, do I really have to look for zeros for this guy? Well, yes and no. If negative 5i was a root, so is 5i. So we get 5i, this is 6, this is 30i, this is negative 16, this is negative 80i, this is 0. Yay! So now we're down to a second degree polynomial. So x squared plus 6x minus 16. Okay. So we were looking for 4. We've already found 2. So let's see if we can factor this out. 1, 16, 2, and 8, 4, and 4. It looks like this is x plus 8, x minus 2. So our other two solutions wind up being positive 2 and negative 8. So at the beginning, we said 4 solutions. Well, they gave us the negative 5i, and we knew the conjugate roots theorem, so we said 5i, and then we were able to find those other 2. You honestly could have found the other 2 through Desmos, since they're real solutions, but all that to say, we have 4 solutions, and we were able to find this other one using the conjugate roots theorem. So that's the theorem. That's how you use it. Here you go.